Is he here? Is he here? Is he here? Peter, where is he? Is he here? Is he here? Do you have him? Where is he? Where?
Him who?
Professor Sprott.
Yes, that's right.
We've looked a lot and we ain't got Sprott. The moving company promised they'd have him here in time for the show. All these people are here. Where is he?
Oh, you know what? Did you check the Chaos Lab?
The Chaos Lab?
Yeah, you know that little lab upstairs?
No. Not more than a dozen times. Of course I checked the Chaos Lab. Look, Peter, call the moving company.
The moving
Call
company.
the moving company. Find out what they've done with Professor Sprott. We've got to get him here.
Let me see if I can find the number. I'll just use the intergalactic stellar transceiver here. See if I can't find him. Aha! There's the number there. Oh, geez, another disruption. Who's there?
Wanna-key.
Uh-oh. Wanna-key who?
Want to keep all these people waiting while you ask silly questions?
Oh, man. Well, Lester, you have brought yet another package to me.
Sign here.
All right. Gee, you're in an awful hurry today. Where are you off to next?
I have to drop off my aunt in Ontago.
All right. See you later. Wow, this is quite interesting. I've never seen one this big before. Why does it say Neptune rules?
Well, will you look at that? They messed up the zip code.
Oh, yes.
All the 6-digit zip codes are on the planet Neptune.
Aha.
That black hole sucks.
Yeah, well, it doesn't take a Stephen Hawking to figure that out.
Well, why don't we open it?
I think we should. Let's just go ahead and open it up. Uh-oh. I think we got a problem here. I don't know. This isn't looking very good at all. I'm not sure if he's okay or not. He does not look very well at this time. It says remove before lecture. I wonder what that's all about. I don't know if he's okay.
No, I think it's all right. This is just what old Doc Onomowak looked like when he was delivered.
Really? How's
Yeah.
old Doc Ock doing?
Well, you know, to tell the truth, ever since he got tenure, he just sits around all day reading comic books.
Ah. Okay.
But all we have to do, we'll just take off his hood.
Yeah, you sure? Okay. I've never done this
And-
before.
Then all we've got to do is spin up his hard drive. He'll be fine.
Okay. As long as you say so. Is this just like this, huh?
Yeah, you take that side, I'll
Okay.
take this side, but Peter, be careful. He's got tenure.
Okay. Ladies and gentlemen, I present to you the autarch of angular momentum, the royalty of rotation, the spirit of spin, a man born to laugh at tornadoes, the king of chirality himself, Professor Clint Sprott.
Welcome to the wonders of physics. Now, we are celebrating our new lecture hall today. We're also celebrating the life of Tom Lovell, my longtime assistant, who for 170 some odd shows helped us with all of the shows. And he wrote many of the scripts and demonstrations. So I'd like to start with a demonstration that involves a volunteer. Who will help me with this? Okay. You, come down here. Tell us your name.
Jim.
Jim?
Yeah.
Okay, Jim, are you a good science student?
Yeah.
Yeah? You don't sound too sure.
Probably.
Yeah? Jim, do you ever go bowling?
Yeah. I went last night.
You went last night. Well, you must be pretty good at it then, huh?
Yeah.
Yeah?
Yeah.
Well, Jim, what we'd like you to do is turn to your right and go over to my assistant, Mr. Wykes. And we're going to make what we call a bowling ball pendulum. A pendulum is any mass on the end of a wire or a string that is suspended from above. And what we're going to ask you to do, Jim, is to hold that right by your nose. Can you do that? And when I say, I want you to let go. Are you ready? Let go. Put your hands down by your side and don't move. Once more. Thank you, Jim. Now, we could do that safely because Jim was, because of the conservation of energy. The bowling ball started with a certain amount of potential energy, and then when it swung out and came back, it came back with almost as much energy, with a little bit being lost to friction. So this is one of the most important principles in all of physics. Now, this was one of Mr. Lovell's favorite demonstrations, and in fact, I believe it was the first demonstration we ever did in this show in 1984. And I called for a volunteer, much as I did today, and I got him down here. And when I was done talking to him, I told him to go over to Mr. Lovell. Now, when I was brought up many years ago in Tennessee, students were taught a lot of respect for their elders. And so we always called our teachers and our parents Mr. and Mrs. And that was the first time I'd ever called Tom Lovell Mr. Lovell, and the name stuck, and he liked it. And so forever thereafter, he was Mr. Lovell. Now, there are many other demonstrations we did with Mr. Lovell, and one of his favorites involved this gadget. Do you have one of these at home? Yeah. What is it? That's right, it's a bicycle wheel. But this one is quite heavy. And one of the things we often do with this bicycle wheel is to stand up on this rotating platform. And I'm going to ask Mr. Wykes to give it a spin, as Mr. Lovell always used to do. And you see, not very much is happening. But if I turn this at 90 degrees, you see it makes me go around. Now I can turn it the other way and go the opposite direction. And so when I was done with this demonstration, I would always hand the bicycle wheel to Mr. Lovell, and he would stop it by pressing it against his shirt. And he went through a lot of shirts that way, so we do it differently today. But another demonstration that Mr. Lovell liked involved a carbon dioxide fire extinguisher. Now I can stand up on the rotating platform with the carbon dioxide fire extinguisher and shoot some carbon dioxide out in this direction, and we'll see what it does. Well, it makes me go around. But you notice, once I'm going around, it's very hard to stop. How do I stop? The other way? Good idea. Let's try that. And this, of course, is the principle on which the rocket works. In a rocket, something goes out one direction, and that makes the rocket go the opposite direction. And that's Newton's third law of motion. Newton's third law is the law of action and reaction. And that, of course, is the way we can travel to distant places in the solar system by using Newton's third law. Now, this is a familiar idea to all of you. Some of you may have a thing like this at home. It's a lawn sprinkler. And if I turn it on, and those of you in the front row may want to duck, except no water is coming out because I'm running this lawn sprinkler with compressed air. But the principle is exactly the same. When the air comes out these little nozzles on one side, the air goes one way. That makes the lawn sprinkler turn around in the opposite direction. And this illustrates Newton's third law of motion.
That was so weak, so puny, such baby stuff. These good people didn't come here to see a lawn sprinkler. They came here to see a rocket.
And I suppose you have such a thing?
I try not to let my mouth write checks that my brain can't cash.
Oh, my goodness. Wait. Who are you?
They just call me Scooter.
Scooter? Well, I can see why. Well, you know, Scooter, you look to me a lot like a very young Tom Lovell, like I remember him 40 years ago.
Oh, really?
Sure did. He had a scooter. Well, his was a little bigger than yours. He rode a motorcycle, and Tom Lovell used to live on a pig farm, and he used to carry a pig on his motorcycle. I see you've got something here you're bringing to us. What is this?
Oh, this is just an old water bottle I found outside the physics building.
You know, Tom Lovell used to bring a water bottle in here, but his had a little bit of liquid in it.
Well, mine does too.
Oh, I see that. And I wonder what that is.
Well, it's probably just water, Professor. I mean, it says right here, bottle for use with water only.
Oh, well, it must be, except, you know, the Lovell would always play a trick on me because he would bring it in and I would say, yeah, that's a little bit of water. And then he would do a demonstration with it that maybe we could replicate that here. He would take that water bottle and he would set it on a track, very much like this. And he would take a match, like those matches, and he would hold the match near that end, and the thing would act like a rocket. But since it's a rocket, we need a countdown. You can't set off a rocket without a countdown. We're all going to do it, starting with 5. 5, 4, 3, 2, 1, lift off! Well, that's just like I remember when Mr. Lovell used to do it.
Wow, Professor, I'm sure glad I didn't drink that.
I'm glad you didn't too, because that, in fact, was not water. It was a little bit of alcohol. And this is how your car works. Not with alcohol, but with gasoline in the cylinder of your car. You mix it with a little bit of air, and then you ignite it, not with a match, but with your spark plug, and it pushes the piston, much like it pushed the water jug there. But these are demonstrations that Mr. Lovell loved to do because he loved rockets and things that were dramatic like that. Now, another demonstration I'd like to show you that involves liquids and gases requires a little orange crush can. And you'll see why I use an orange crush can in a moment. It's empty. There's a hole in the top. And all I'm going to do is put a little bit of water in it, maybe about a half of an inch of water in the bottom. And then I'm going to set it over a burner here and turn on the fire and let it heat up. Now, this is a nice demonstration because you can do this at home. Maybe you don't have a burner like this, but you do have a stove, don't you? And you probably have cans like this. And so you could put a can with a little bit of water on it and put it on your stove and bring the water to a boil. Now, of course, it takes a while for this to happen. So while I'm waiting for the water to warm up, I want to show you another demonstration, and then we'll come back to this. The demonstration I want to show you involves two hemispheres. A hemisphere is half of a sphere. So this is a hemisphere, this is a hemisphere. You put them together and you have a sphere. Now, these are not attached in any way. They just touch each other. There's a rubber gasket in there. But they're not attached. And the reason I want to do this is because I can now take all of the air out of the inside of this. And to do that, we use a vacuum pump. And I just happen to have a vacuum pump here. So we'll connect that to the nozzle on one side. And we will turn on the vacuum pump. And you will see the pressure coming down on this gauge. When it gets down to 0, we know we have removed all of the air from these hemispheres. Well, it takes forever for it to get down to 0. In fact, it never will completely. But after a while, it gets down close enough that we can do the demonstration. So now what I want to do is close this valve right here. Once that valve is closed, we don't need the vacuum pump, so we can turn that off. In fact, we can let air into the vacuum pump. And then we can take the hose off. And I'm going to take this nozzle off. And in its place, put a handle, like so. And then I want someone that looks kind of strong. How about you? You look strong. And let's see if we can pull it apart. Not really. Now, let me open the valve, hold it, but don't let it drop. And finally, it came apart. And that's because the pressure of the surrounding air was pushing in all directions around this. Air pressure at the surface of the Earth is about 15 pounds per square inch. And that's just the weight of a column of air that goes all the way to the top of the atmosphere. And so there's about 300 pounds of force holding these together. And so if we hung it from the ceiling and someone who weighed about 300 pounds hung from it, it would come apart. But it takes quite a bit of force to pull them apart. Now, these are called Magnetism hemispheres, after a little town over in East Germany, where several hundred years ago, the mayor of Magnetism, who was an amateur scientist, used to do this demonstration for the townsfolks. And he used an 18-inch diameter sphere, and he had 2 teams of horses, and they couldn't pull it apart, showing how very much pressure the atmosphere can exert. So let's see how our little can is doing. We have now brought the water to a boil, and as a consequence, there is some steam in the can. So there's liquid water, but there's also gaseous water, and that's what we call steam. And once the water begins to boil, the steam forces the air out of the can. And so after a while, the can has mostly liquid water and steam and very little air. Now what I'm going to do is take the can off the burner, and I'm going to turn it upside down in a little tray of water right here. Now, if you were doing this at home, you would just use water in your sink, but I want to caution you, this can is extremely hot, so you certainly don't want to touch it. And so when we do it here, I use these tongs. Maybe you don't have anything quite like that at home, but you probably have some hot pads or something that how you could safely do this. And so we'll turn the burner off, take a moment for that to go off, and then I'll take this and invert it in this tray of water. And now you see why we used an orange crush can. And what happens is that the steam condensed back into liquid water, and the liquid occupies a much smaller volume than does the gas. And so it left a partial vacuum in here. And so the pressure of the atmosphere on the outside pushing in all directions crushed the can with 15 pounds per square inch of force pushing in all directions. This demonstration with this can be done in a very large scale. And in fact, a demonstration very much like this has even been done on The Tonight Show with Jay Leno.
Welcome back. My next guest, a good friend who teaches physics at the University of Pittsburgh in Johnstown. He's back to show us some incredible science experiments. Please welcome our mad scientist, David Willey. David, come on out here. Good to see you again.
Thank you, sir.
What are we going to do today? What's first?
We got 3 really neat demos, all to do with air pressure. This one's the first one.
The first one here?
Yep.
Now, what is this? We have a kiddie pool. What is this?
This is an ordinary 55-gallon drum, and we got a kiddie pool with some water in it.
Right.
We're going to collapse the drum using air pressure.
It can't be done.
It can. We gotta fill it with steam first, though.
You got to put steam in it?
Yep. Gotta put steam in it.
What do I need to do?
Well, what you need to do first is put a pair of gloves on.
Put a pair of gloves on. Ooh.
The steam is
quite a winter coming up, huh?
Really, really hot. Yeah, I hate it when my doctor does this bit.
All right, yeah.
And what I need you to do is you're going to be the other side.
All right.
And you see that counterweight there, okay?
This here?
Yep, that one there.
And what do I do?
In about 20 seconds after I've started filling this with steam, I'm going to need you to lift that so that it drops this drum into the paddling pool.
Right from here?
Yeah, but not yet. Okay, first I've got to fill it with steam.
Okay, let me see how I do. Okay.
There we go. Now, got to get it to the right hole here.
There we go.
Okay. And I'll give you a count of 3.
And just lift it up.
We got to get it full steam. There we go. A little bit of water to be purged out first. And we should get some steam coming through here.
Yeah.
And it takes just a little while because we've got to get the can hot. Because the idea is when the steam condenses, there's going to be a vacuum inside this can.
Okay.
Okay, now we're almost at a point where we can do it. We've got some good steam coming out.
Yeah.
Okay. 1, 2, 3.
Wow, that's pretty good. Wait, let's see it in slow motion. Wow, that's pretty good. Wow.
Thank you. Thank you. Yeah,
So I showed you that demonstration because last weekend, David Willey, the mad scientist from The Tonight Show, was here with us. And he told me a number of things I didn't know. He's been on The Tonight Show 16 times, and he's done over 50 demonstrations. And many of the demonstrations he did on The Tonight Show, he got from the wonders of physics. And we're going to try to get him back next year to do a little more of his demonstrations for you, so I hope you'll come back next year and see that if, in fact, we succeed in doing that. But he did leave me with a number of demonstrations that he has done on The Tonight Show, and these are demonstrations I've never done before, and so I want to show you a couple of them. Here I have a bucket that has in it a little bit of soapy water, and I have a tube that goes down in it that has methane in it. And I'm going to make some methane bubbles. Now, methane, as you know, is the gas that you have in your homes. If you have a gas furnace or a gas stove, it may run on natural gas, which is primarily methane. Now, what I'm going to do is light a flame here, because as you know, methane is a flammable gas. And I'm going to take a tennis racket with a little bit of aluminum foil on it, and I'm going to take some of these nice methane bubbles we're producing here and get them on the tennis racket, and then I'm just going to put them in the flame. That was pretty neat, wasn't it? Do it again? Well, I'm glad you asked. Now, David Willey did that demonstration on The Tonight Show, and when he did it, he had Jay Leno hold the bubbles in his hand, and he burned all the hair off the back of Jay Leno's hands. So I figured that's maybe not a good idea. Well, I want to show you now another demonstration that David Willey did when he was here last week. He likes to do things with balloons and with liquid nitrogen. So here's a balloon that's blown up with ordinary air, and what I'm going to do is put it in this little dish, and then I'm going to pour some liquid nitrogen over it. Now, liquid nitrogen is a liquid that looks a lot like water, but it's extremely cold. It's at a temperature of about 321 degrees below zero Fahrenheit, or 196 below 0 Celsius. And when you cool the air down to that low a temperature, it contracts and it occupies a very small volume. In fact, some of the air becomes a liquid. Now, what I'm going to do is put this over here, and if you'll just blow gently on it, you see as it warms up from her breath, it gets larger and larger. And eventually, it'll be at the temperature of the room, and it will be back to its regular size. Would you like to see it again? Okay, well, I do have a second balloon here. I need some more liquid nitrogen. So we'll take this balloon, and we'll pour the liquid nitrogen over it. And similarly, it will get smaller, much as the other one did. And now that you know what you're supposed to do, I'm going to ask for someone else here on the front row to blow on it. How about you? Just blow on it very gently. Warm it up. Oh, oh my goodness. Well, that balloon, in fact, was filled with helium, as you suspected. And it went up to the ceiling, and it will remain there for quite a while. Now, another demonstration that David Willey did for us involved a very familiar material, coffee creamer. And I can take a little spoon of it, and I want to demonstrate to you that coffee creamer is not flammable. I can put it in the flame here, and it doesn't burn, right? But he did a curious thing with the coffee creamer. He took a little funnel like this with a hose on it, and he put some of the coffee creamer in the funnel, something like this. So we'll put a little bit in. Now, if a little bit's good, a lot is better, right? Okay? You want more? Okay, that should be enough. And what he did was just blow through the tube and make the coffee creamer come out the funnel here, and we'll see what happens. That was pretty neat. Would you like to see it done again? Why did I think you would say that? More? Cover your ears. And as you might have suspected, those balloons were not filled with helium, even though they're rising, but they were filled with hydrogen. And hydrogen is a flammable gas. And when the flame came near the hydrogen, then it set the balloons on fire, and there was, in fact, an explosion. Now, I was about to show you a demonstration over here that also involves boiling water and heat. In this flask, I have a little bit of water, about up to there, and there's a burner underneath it, and I'm going to light the burner and heat the water. Now, as you know, it takes a while for the water to come to a boil. And so we're going to have to wait, and we'll open this valve so that the steam can come off. And so we'll just let that boil for a moment, and then we'll come back to it in a minute. Well, who are you?
Well, I'm Petty Pessimist. Who are you, and who are all these people?
Well, I'm Professor Sprott, and this is the Wonders of Physics.
Wonders of physics, more like blunders of psychics. This is that demo show, isn't it?
Oh, yeah, this is that demo show.
You can't possibly tell me these people are having fun.
I think these people are having a great time, and I bet I could prove it to you.
Okay, prove it to me.
Okay, everyone is having a good time. On the count of 3, yell as loud as you can, "Physics is fun." Are you ready? 1, 2, 3. How about that?
I don't believe it. Well, what are you doing here anyway?
We're boiling some water.
Boiling water? What are these people through? I learned how to boil water in my physics class. I nearly fell asleep. As I recall, it was something like this.
And now we boil water.
See, you can't tell me this is going to be interesting.
Well, I suppose most everyone has seen water boil before, but have you ever seen water boiled with ice?
Of course not. You can't boil water with ice. It takes fire to boil water. See, fire, boiling.
Well, sometimes you use fire to boil water, sometimes you use ice. Today we're going to use ice.
Okay.
And if you'll give me a hand, I'll show you how we do it.
All right.
So first I'm going to turn off the fire. And of course, after a while, the boiling will stop, as you would expect.
Yep, it stops.
Well, not quite yet, but soon. What's this stuff coming off?
Looks like steam or vapor.
Looks like steam, but steam's actually an invisible gas. What you're seeing is when the steam comes in contact with the cold air, it condenses back into tiny droplets of liquid. And that's what we call a cloud. Now, has the boiling about stopped there?
Pretty much.
Pretty much. One or two little things.
Now
when that happens, I'm going to close this valve, and then I want you to take a handful of ice and put it right on the top of the flask there.
Okay.
Go for it.
And this is going to boil, huh?
We'll see.
I don't believe it.
It's really cold, isn't it?
It is cold.
It's ice, huh?
It is ice.
Yep.
That's for sure.
See something happening in there?
Yeah.
What is it?
It's boiling.
What did I tell you?
I guess you're right. So that's pretty cool. How's that work?
Well, when the steam condenses into liquid water, it leaves a partial vacuum. You've probably heard that water boils at a lower temperature when the pressure is lower.
You mean like in Colorado or something?
Like in Denver. People there know about this.
Yeah.
Well, the pressure was reduced so much that the water boiled at the temperature of the ice.
So that's pretty cool. So what else are you doing here today?
If you think this is cool, you stay around. We'll show you some things that are really cool.
Promise?
I promise.
Okay. Maybe I'll just take one of those seats over there.
I think that's a great idea. Well, indeed, you can boil water with ice, and you may not have seen that before, but I did this demonstration about 2 years ago, and I spilled the hot water on my hand, and it didn't do me any harm, but my hand hurt for the next lecture that I did, and so I did the whole lecture with my hand in a bucket of water, and Mr. Lovell was literally my right hand. because every time I needed something with both hands, he would come running over and would give me a hand, quite literally. So I did this demonstration because it reminds me of that story about Mr. Lovell from about 2 years ago. So another area of physics that I like to tell you about involves sound. You've heard a lot of loud sounds today already, haven't you? Over here I have a gadget that is wiggling up and down in response to my voice. Do you know what this is called? That's right, an oscilloscope. And if you can't see it down here, you'll be able to see it up there. And what you're seeing is what a sound wave would look like if you could see it. Now, normally a sound wave is invisible. When I'm talking and you're listening, there's a wave in the air between my mouth and your ears that is going back and forth. And it looks something like that, except it's invisible. And so we make it visible here because this oscilloscope is connected to this microphone right here. So any sounds that come into this microphone are displayed there. And you can see how complicated is the wave that corresponds to human speech. But not all sounds are so complicated. Here I have a device that makes a much simpler kind of sound. You recognize this? It's a tuning fork, a little U-shaped piece of metal. I strike it with a mallet and it makes a sound. And I want you to look on the oscilloscope at what the sound looks like. And you can see it's a very regular kind of oscillation. It goes up and down in a very regular way. This is an example of a very pure sound. It's called a sine wave. And this is the musical note A, or about 440 cycles per second, or 440 hertz. And tuning forks are very useful because they make very precise pitches. Now I have here another tuning fork that is tuned to a slightly different frequency because there's a little weight on one side of it here. See if you can hear the difference. Can you hear the difference? You think so? It's very similar, but a little bit different. Now, what do you think would happen if I would strike them both at once? Let's try that. And watch on the oscilloscope. I'll put the microphone over here so you can see. Can you hear that funny sound? It goes woo, 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 woo. And those are called beats. Whenever you have two frequencies that are almost the same but not quite, they add and subtract so that sometimes they're loud and sometimes they're soft. So it gets loud and soft several times every second. And in fact, the beats are going up and down at a frequency that's just equal to the difference of the two frequencies. Now, musicians know about this because they often tune their instruments that way. One musician will play a note, and the other musician will play the same note and then adjust the strings in the violin or whatever so that the beats go away. And when they do, you know they have exactly the same frequency. Now, while we have two tuning forks out here, there's another very interesting thing I can show you. I'm going to take this weight off of this one so that they are tuned to exactly the same frequency. And I'm going to strike one of the tuning forks and let it vibrate for a moment, and then I'm going to stop it from vibrating by simply grabbing it with my hand. And let's see what happens, and watch on the oscilloscope. Now that's pretty odd, isn't it? I didn't strike this one at all, and yet it was making a sound. So what's happening? Well, this one was making a sound wave. The sound wave was traveling through the air, and it was being picked up by this one, and it set this one into vibration. This is exactly what happens when I'm talking. Your eardrum is vibrating in response to the vibrations of my vocal cords. And this works because they're tuned to exactly the same frequency. So it's a little bit like a radio transmitter and a radio receiver. You know, you don't hear what's being sent by the transmitter unless your radio is tuned to the right frequency. If you tune to a different frequency, you don't hear it. And I can illustrate that by retuning this, by putting this weight on and making it a slightly different frequency, so slight that you can hardly tell the difference. And I'll strike it again, and we'll see if it sets this one into vibration. So that would correspond to the case where the radio receiver is tuned to a different station. Now, do you know that there are sounds that you can't hear? Do you know an example of one? A sound that you can't hear. What? Dog whistle. A dog whistle. Very good. It just happens that I have right here a dog whistle. Now, a dog whistle makes a sound, but it's at too high a frequency, or the pitch is too high, for your ears to hear. This makes a sound at about 15 or 20,000 cycles per second. Some of you may be able to hear it, but most people can't hear it. But dogs can hear it all too well. And to prove that there's really a sound, I'm going to do it near the microphone and let you look on the oscilloscope. So here we go.
You're the one pestering my poor little pooch.
Your poor little pooch. Well, who are you?
I'm Complexity, and this is my little dog, Barkley. And, oh my goodness, look at this mess. This looks like a physicist's desk. It's chaos, utter chaos. Oh, hold on a minute, I think that's me.
I hate it when my students' cell phones go off. This had better be important. And talk about complexity.
Yeah? Yeah? Right now? I suppose so. Okay, bye.
Now, who was that was so important?
That was my grandmother, Necessity.
You have a grandmother named Necessity?
Well, yeah, haven't you ever heard that necessity is the mother of invention? Well, I'm Complexity, the daughter of invention. And I'd love to stay and chat about the subject, but I really have to go. Necessity calls. Come on, boy.
Well, I guess it never occurred to me that Necessity would have a daughter as well as a mother, but I guess she did. But she did say that she saw chaos on the bench here, and in fact she did, because I have a demonstration here of what we call chaos, and that's something we study in physics. I have here an electrical circuit that's a little bit like the tuning fork. It makes a very pure sound. It's a sine wave, and you can hear the sound, and you can see on the oscilloscope what that sound looks like. Now, I have here a volume control, and I'm going to turn that up, and you'll see a very curious thing happen when I turn it up just a little bit. Suddenly, there's a new frequency that comes in that's just half of the original frequency. It's 1 octave lower for you musicians. And this is a signature that chaos is about to onset. And if I turn it up a little bit more, you'll be able to hear the sound of chaos. And if I turn it down, it will go back to a pure sine wave again. Now, I'm sort of proud of this circuit because it's one that I invented. And other people have made other similar circuits, but this is a particularly nice one, and you can even buy it commercially. And this circuit, if some of you are interested in, is actually described in my brand new book, Physics Demonstrations. And I don't usually try to sell books in the Wonders of Physics, but this is an effort that's been going on for 20-some odd years, trying to document all of the demonstrations we've done over 22 years in the Wonders of Physics. And so in here, there are 85 demonstrations with 3 hours of DVDs before a live audience. And if you're interested in that, they have them out in the lobby, and you might want to look at it after the show, as well as many other things we have there as well. So speaking about electricity, electricity, of course, is a very favorite topic because there are many fun things we can do. And for the next demonstration, I will need a very brave volunteer. Come on down here. You look very anxious. Come down here, and what's your name? Sean. Sean, okay, Sean. Now, Sean, you like electricity, I gather. Do you have it at your house? What do you use it for? Must be something.
The telephone?
The telephone, yeah. Telephone uses electricity. How about lights? Do you have electric lights?
Yes.
Yeah. You know, has the electricity ever gone out at your house?
Yes.
And there's a lot of things you couldn't do, right? So electricity is very important. Have you ever been out in a lightning storm?
Yes.
Does it scare you?
A little.
A little bit. Well, we'll try not to hurt you, but we're going to take you to a lightning storm. You're feeling brave, right? Okay, turn to your left and walk right over to this cage. And have a seat in what looks very much like an electric chair. Now over to Sean's right is a 1,000,000-volt Tesla coil. and it makes bolts of lightning. So I'm going to turn it on, and as long as you don't stick your fingers through the cage, you shouldn't feel a thing. Thank you, Sean. Now, he was safe because he was inside of what we call a Faraday cage, named after Michael Faraday, a famous chemist and physicist who lived about 150 years ago, and who used to do demonstrations of this sort to the public. Now, with a 1,000,000-volt Tesla coil, there are many interesting things we could do. And the next thing is far too dangerous to ask for a volunteer. So we're using one of our assistants, Mr. Paul Nahn, who has helped us from the very first show we did 23 years ago. And when he was the age of some of you, he used to make Tesla coils. You can build these. And Paul has helped us for many years with this demonstration. Now you notice he's putting a crown on his head, a metal crown, and you may wonder what that's for. Believe it or not, that's a lightning rod. On that crown are a bunch of little points, and that's just what you do when you put lightning rods on your house. Because if any sparks come off of Paul, we want the sparks to come off of the metal crown and not directly off his skin, where it could injure him. In fact, Paul used to have lots of hair until we burned it all off. No, I just made that up. Anyway, Paul is also putting thimbles on his fingers. They're metal thimbles, and they have points on the end. And it's for very much the same reason. Because if any sparks were to come off his fingertips, it could burn the fingertips. And to prevent that from happening, he puts a little piece of metal on, and then the sparks come off the metal tips. But the electric current, nevertheless, passes through his body. Now, he's taken his shoes and socks off, and he's climbing up on an insulated platform in a metal tray connected by a copper tube to the terminal of the 1,000,000-volt Tesla coil. Don't do this at home. You'll see why we call Paul Nahn the human voltmeter. Now, Paul is very brave to do that, and you notice he's taken the thimbles off his fingers. So, in order to protect his hands, we'll give him in one hand a 2,000-watt light bulb. In the other hand is a discharge tube, much like a fluorescent tube without the coating on the inside. And once again, you will see Paul Nahn, the human voltmeter. Okay, so that's a very dramatic electricity demonstration. And I want to show you another electricity demonstration over here. Back here behind the lecture bench, I have what we call a capacitor. A capacitor is like a large battery. It stores electric energy. And what I'm going to do is charge this capacitor up to about 5,000 volts, and then I'm going to discharge it into a little strip of aluminum foil, much like the aluminum foil that you have in your kitchen at home. Now, this can make a little bit of noise, so I'm going to put my ear protection on. And I'm going to put my safety glasses on. And we will charge this up. Now, when it comes up to about 5,000 volts, I'm going to discharge it into this aluminum foil. So if loud noises bother you, you may want to do what Mr. Wykes is doing and cover your ears. So is everyone ready? Here we go. Well, it seems not to have worked, but that's okay. Our new lecture room is equipped with a do-over switch. Whenever a demonstration doesn't work, all I have to do is close the switch, it runs time backwards, and then the demonstration is repeated. Now, you may feel a slight tingling in your fingers when I do this, but that'll go away by tomorrow. So is everyone ready?
Yep.
Oh.
Hey, Sprott, you blew all the fuses.
Professor Sprott? You've lost power again?
Well, who are you?
Well, I'm Rusty Kilowatt, of course, inventor of the blackout. I'm surprised you even had to ask. We've met so many times before. Like, there was once, I think you and Mr. Lovell were working on the toka pole, maybe?
All right, Sprott. I bolted down the stochastic field lines. I hope this works. Good work, Bubble. Now stand clear. I'm going to close this switch, which will start the plasma guns. Then we'll see if we get fusion. Wait! Sprott, that's not the plasma gun switch. That's the pizza switch. It tells the pizza company that we need more pizza. If you connect the toka pole to the pizza company, we'll have some hot peppers on Park Street tonight. Nonsense, Bubble. Nice work, Sprott. Would you like drinks with that?
Yeah, that's how I remember it. Well, don't cause any more blackouts today, Professor Sprott. I'm a very busy man. I'm headed east now to make sure the scientists at MIT and Princeton don't get fusion either. Let there be light.
Well, it is true that Tom Lovell and I spent many days out at the barn with very high power electronics, and we did have a lot of explosions like that. In fact, once we had a bank of about 30 of these capacitors charged up to 5,000 volts, and we discharged them into the AC power line. And we blew out every instrument in the lab. And Tom and I stayed up all night repairing all of the equipment so that people wouldn't know that we'd done it when they came in the next morning. But fortunately, we have a do-over switch for the do-over switch. And so if I just open that again, I can put on my goggles, and we can try to repeat the demonstration. So we'll charge the capacitor bank up to about 5,000 volts. You see it coming up to about 3,000 volts. And when it gets up to 5,000, I'm going to discharge it into this foil of aluminum. So if loud noises bother you, cover your ears. Is everyone ready? Yeah. Here we go. And you see, all of that electrical energy went into that aluminum foil, and it was converted into heat. And it heated it up so much that the aluminum foil evaporated. It became a gas. And then it eventually went back into a solid, but no longer a strip of aluminum anymore. This demonstration is an electricity demonstration, but it is closely related to a subject of magnetism, because magnetism and electricity are related to one another. And I want to show you a demonstration that involves magnetism over here. Now, about 200 years ago, they used these for a different purpose, but for our purpose, it's a cucumber slicer. In our laboratory, we eat lunch like the rest of you, and of course, sometimes we need to slice a cucumber. And so we use an apparatus like this. It has a very heavy and sharp copper blade. And I'm going to put the cucumber underneath the blade, and Mr. Wykes is going to raise the blade all the way to the top and then release it. And that's how we slice them. Now, I want to repeat this experiment, but this time I'm going to use a carrot. So we also slice our carrots this way. Now, I want to call your attention to the fact that Mr. Wykes is now going to place 4 very powerful magnets just behind the blade. Not where they touch it, but where the blade will come by very close to the magnets. Now, I want to call your attention to the fact that copper is not a magnetic material. Here's a permanent magnet, and it's not at all attracted to the copper. And to prove that it's a permanent magnet, I can easily lift some nails with it. But when the copper moves rapidly by the magnet, it will momentarily be magnetized, and there will be a force acting on it. So let's try that again and see if we can slice the carrot. Well, it put a little nick in the carrot, but it didn't slice through it because the magnet stopped the blade just in the nick of time. So that illustrates how powerful magnets can be. But those are permanent magnets. Another way to make magnets is with electric currents. So here I have two coils of wire. There's an orange one and a blue one. And in a moment I'm going to turn it on, and there's going to be a very large electric current flowing in these two coils in opposite directions, as it turns out. And here I have an aluminum ball about the size of a softball. It's hollow, so it's not too heavy. And aluminum is also a material that's not attracted to a magnet. Here's another magnet. See, it easily picks up nails, but not at all attracted to the aluminum. But when I put the aluminum ball down in the magnetic field will be rapidly changing, and that will induce electric currents in the ball and make it magnetic, which is not at the moment. So we'll turn that on, and we'll let it go. And you can see how it is magnetically levitated. It's suspended in such a way that it's not touching anything. Now I can also do that, not with a sphere, but with a cylinder, like this, also hollow, also made out of aluminum. And it's sort of neat to see because when it spins around, it's a little prettier, I think. And this is one way one can make motors with bearings that have very little friction because nothing touches anything. And in fact, people make, over in Japan, for example, they have trains that are magnetically levitated using this principle. So that illustrates how powerful magnets can be.
If the women don't find you handsome, they should at least find you handy.
Well, now, who are you?
I'm red duck green tape.
Well, I do see red and green and duct tape, but where are you from?
Well, I just wandered down from the Opossum Lodge way up north to see the Wonders of Physics show.
Well, you're certainly in the right place, and you're a handyman, and that's good because it turns out our coils weren't working very well. Can you change the inductance on these coils a little bit for me?
Inductance.
Right.
That ought to do it.
Oh, inductance, not duct tape.
Oh, well, I am a handyman, not an electrical engineer.
Well, I can see that now. But I see you brought something here. What is this?
Oh, well, some of the gents up at the lodge said you were going to do a demo with a Chrysler tube.
Chrysler? That's a car. I bet they meant a Geisler tube. We're going to do a demonstration with that.
Well, that must be what those guys are talking about.
Well, if you just left your Chrysler tube here and have a seat, I can show you a Geisler tube if you like.
I'm pulling for you. We're all in this together.
You sure are. Because indeed, over here, I do have a bunch of little tubes that are called Geisler tubes. Geisler was a man who lived about 100 years ago, and he was a glass blower. And he discovered if you took long glass tubes that were hollow, and you took all the air out of them and put a little bit of inert gas in, and put an electric voltage between the two ends, that they would glow. And then he made a bunch of funny shapes, and he was able to change the gas to make them glow different colors. And now we call these Geisler tubes, and they're very pretty. I'm going to turn these on and show it to you. Now I show you this because the gas in those tubes is something called a plasma. And a plasma is a gas that's been heated to such a high temperature that it's an electrical conductor. And turns out that most of my professional career I studied plasmas. And Mr. Lovell was the chief engineer of our plasma physics group for his whole professional life. So he spent a lot of time making devices that produce plasmas and confined them and studied them. And so that's very important. Those sorts of demonstrations are very important to him. So we always conclude these shows with one last demonstration. And that involves this liquid nitrogen that I showed you before. The same liquid nitrogen we used for the balloons, except we have a very large container of liquid nitrogen. I'm going to force nitrogen gas into this. That's going to cause the liquid to come up into this pipe on the top, where it will come out a bunch of holes on the top. Now the nitrogen is very, very cold. So when it comes in contact with the air will cool the air, and the moisture in the air, the water vapor, will condense into tiny droplets of liquid water. And that's what we call a cloud. And this demonstration has also made it to the Tonight Show with Jay Leno.
Huge amount of noise.
Okay.
We are going to make some
It doesn't seem to be switching
clouds at ground level.
What is this?
This is liquid nitrogen. This was a demonstration a good friend of mine, Dr. Sprott, showed me how to do this.
Now, Kev, you have a bong like this, right?
Thank you very kindly.
Now, what is
I'm
this,
gonna
nitrogen?
Turn this on. This is spraying liquid nitrogen.